All right, so 3.7, we're looking at rational functions, all right? And so in 3.7 part 1, we looked at a very special type of rational function, right? And so maybe we make note here for ourselves that one special type of rational function is the reciprocal function. Okay, so the reciprocal function is just a special type of a rational function. And we did that one in 3.7 part 1, so we could think about how all these graph transformations that we've been studying actually apply to pretty much any graph or any function that we have. Okay. So let's talk about rational functions in general. Like when we zoom out, what is a rational function even? Why does it matter? Okay. So a rational function is nothing more than the ratio of two polynomial functions. So all those polynomials we studied before, like x cubed plus 2x plus 7, or x to the 5th minus x to the 4th plus 1. All of those are polynomial functions. But what we do, like, where does a rational function come from? Well, it turns out that we just take two polynomial functions and we divide them. And that's how we end up with a rational function. Okay. So we take some polynomial function, we divide it by another polynomial function, and then we get a rational function. Okay. So our rational function is this part, like the output. But how did we get it? We took a polynomial function and then a different polynomial function, and we divided those. Now, why would I make a big deal of saying q of x can't equal 0? Because that's actually really important here. Why would I take the time to say q of x cannot be 0?
Is it because it gives an error?
What do you mean by an error? Tell me more about that.
Well, I remember from part 1, in the very first example, we couldn't have 0, like 6 over 0, because it gives us anything divided by 0 is an error.
Perfect, perfect. And that's exactly the point here, is we sort of know these little rules like, oh, we can't divide by 0, right? But then when do we use it again? And it turns out this is one of those times. Okay, so even though this might look like, wow, this is like super fancy math, and we're saying we're using all these letters and we're saying q of x cannot equal 0, all that means is that our denominator cannot equal 0. Otherwise, f of x will be undefined. Okay. And undefined is just a more mathematical way of saying there was an error, right? We're classifying it. We're saying it's undefined. That's the kind of error that it is. And so in this class, what we're going to focus on is figuring out how do we connect the equations and the graph, right? Meaning here's an equation. How could we guess what the graph is going to look like? But also here's a graph. Can we figure out how we got or where the equation was that it came from? Okay. And more specifically, as you're studying, you really want to think about these two vocabulary terms. One is called end behavior, and the second one is called discontinuities. All right, so I'm going to be asking you a lot about, tell me about the end behavior, tell me about the discontinuities. Okay. So what do those mean? Let's take a very brief look at what these mean And then I think we'll probably take a break before we jump into a bunch of examples. All right. So end behavior. Let's think about end behavior. All right. So it turns out that in addition to a polynomial, right? So if we think about a polynomial, what were our options for end behavior?
You had up, up, down, 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 up, and then up, down.
Perfect, right? For polynomials, we had 4 choices. Either both ends were going to go up, both ends were going to go down, one was going to go up and down and the other's down, or the other way around, right? Those were our 4 choices. And so when we're thinking about that though, if we're combining 2 polynomial functions by division, right? We're dividing them, we're finding that ratio. It turns out that we're going to have some other choices for end behavior, all right? And in particular, we can break these down into 3 choices, all right? So one thing that we're going to be making sure we know how to do is looking at the degrees. So how do we find the degree of the numerator and the denominator? All right. So if you think back to earlier in chapter 3, and I was like, what's the degree of this polynomial? What's the degree of this polynomial? This is another way that we can use the degrees to tell us about a graph. Okay. So what is this first case? Well, it turns out that if the degree of the numerator is less than the degree of the denominator, we end up with the function will always give us a horizontal asymptote at y equals 0. Okay. It turns out that if the degree of the numerator is greater than the degree of the denominator, then we're going to have no horizontal asymptote. Okay. Your textbook is a little bit specific in saying that the degree of the numerator is greater than the degree of the denominator by 1. And all I want us to know about that piece is if that degree is greater by 1, then we have something called a slant asymptote. Okay. But in general, if the degree of the numerator is greater than the degree of the denominator, there's just going to be what we say no horizontal asymptote. Okay. The last case is what happens if the degrees are equal to each other. Like the degree on the top is 2 and the degree of the bottom is 2. It turns out we will have a horizontal asymptote. And we can find that equation just by finding the ratios of the leading coefficient. Okay. And so what I want to do right now is just walk through maybe like 3 quick examples. So you can practice telling me, is the degree of the numerator less than, greater than, or equal to the degree of the denominator? Okay. So we'll squeeze these in right here. Let's take a look at example right here. And let's say that you had this equation, 3x f of x equals 3x squared minus 2x plus 5 over 18 minus 6x squared plus 12x. So in this case, can someone tell me what the degree of the numerator is? Yeah, I would agree that the degree of the numerator is 2. Right, so degree of numerator is 2 because 3x squared is the term with the highest power, right? So 3x squared, that's the one with the highest power. The power is 2, so the degree is 2. what would we say about the degree of the denominator? Why is the degree of the denominator 2?
My reasoning was just that it's the biggest degree in the denominator.
Exactly, right? The same reason that we had before. And so the degree on the top is 2. The degree on the bottom is 2. And so if we reread this rule, the green one, it says that the degree of the denominator is equal to the degree of the numerator. If that's the case, then the horizontal asymptote is the ratio of the leading coefficient. So my horizontal asymptote, should I write x equals or y equals?
Y equals.
Good, we're gonna write y equals. What is the leading coefficient of the numerator? Three, okay. What is the leading coefficient of the denominator? -6, okay. So the 3 is the coefficient for 3x squared. But the reason why we don't want to choose 18, even though it's in the front, is because we need to pick the coefficient of the x squared term, meaning we want to choose a -6, not just the first one we see. It's the coefficient of the highest degree term, so -6. And we could simplify this and say the horizontal asymptote is going to be at y equals -1/2. Right? So this would be an example of that last rule, the degree of the denominator and numerator are equal. So then we take the ratio of the leading coefficients to find that horizontal asymptote. Okay. I'm going to change this equation. I'm going to keep the numerator the same. And what I want you folks to do is I want you to change the denominator so that we end up with the pink case. Yeah. So take a moment, type into the chat, what do you think I could put in the denominator? What polynomial do you think I could put in the denominator to make the horizontal asymptote be y equals 0? All right, I see a 1/2. Do you mean just replace the entire denominator with 1/2?
Oh no, I mean, you would have it be x minus 1/2 or x plus 1/2. I can't remember right now, but the 1/2 is next to the x.
Oh, you mean like this?
Yes.
Okay. What are our thoughts, folks? We've got an idea thrown out there, brave idea put out there. What do we think? Do we think this matches the pink case, which is that the degree of the numerator is less than the degree of the denominator?
I think that would be less than. You'd have to like factor the denominator and get at least 2 factors.
Okay, so if we look at this for a moment, I think we would agree the degree of the numerator is 2, right? We said that earlier, that the degree of 3x squared minus 2x plus 5 is 2. what degree could the denominator be to make the pink case be true? I think a degree 3 would work because 3 is bigger, or let's say it the other way, because 2 is less than 3. Right? So we want the degree of the denominator to be bigger than the degree of the numerator. What else would work? Maybe we do degree 7 on the bottom. Sure, the bottom could be degree 7, right? So degree of denominator could be anything long as it is larger than 2. So Elisa, that is a great way of saying that. Any degree greater than 2 will work. So we could even do something like this. Now I've made the denominator degree 3. That totally works, right? You could say, oh, Avi, why are you bringing up fractions so early in the morning? And you could just say, couldn't I do that? And that would be fine also, right? But this, or x plus 1/2 to the 3rd, that would work. Or x plus 1/2 to the 17th, that would work. But in all of these cases, we get our degree on the bottom is bigger than the degree on the top. So then we end up with a case where we're always going to get a horizontal asymptote of y equals 0. Let's try one more. This time, I want you to create an entire rational function, top and bottom, that would match with the orange case, where the degree of the numerator is greater than the degree of the denominator. It doesn't have to be by 1. It just has to be the degree of the numerator is greater than the degree of the denominator. I love it. All right, we see one that has like a 3rd power on the top, the 2nd power on the bottom. You can make this as fancy as you want. So we can put something just like Matt has put in there, 4x cubed minus 2x plus 1 over x squared, right? But sometimes it's okay to just be like, I just need the power on the top to be bigger than the power on the bottom. And I think something like that is equally as clever because you really nailed it, right? This is the point. The point is that the degree in the top is going to be bigger than the degree on the bottom. This would be absolutely fine. And I don't know about you, but I know sometimes when someone's like, make up a function, I'm like, I don't know. I just like kind of freeze. It feels like something that's really hard to do. It's okay to say simple as long as it matches the rules, you are good to go, okay? And so in this case, we would say that there is no horizontal asymptote. All right. So great job thinking through these different examples here, right? And I can see something like this being, oh, I don't know, a really great group portion of the exam kind of question where I want to hear different ideas, right? I want it to be something that's worth talking about with each other. How many different functions can we create? And what is the common thing that they all share, all right? And so before we go on break, let's talk about the second characteristic of rational functions that I really want us to know about, and that is discontinuities, all right? Now you'll notice that the end behavior just had one, right? It was end behavior, 3 different cases. But there are actually 2 different types of discontinuities here, all right, that I want us to make sure we know how to recognize. So the first one is a discontinuity that happens when we take a number and we divide it by 0, okay? So what does this mean? This is actually where our vertical asymptotes come from. Come from a number divided by 0. Okay. In other words, we're saying find, in other words, Q of X equals 0 will help us identify vertical asymptotes, right? And in particular, this Q of X is the one we set up here. Where is the denominator, right? So when Q of X equals 0, right, the X values that make Q of X equal to 0 will be our vertical asymptotes. All right, how is that different from this other case? Okay, so sometimes we'll try and plug something into the calculator, but specifically, it's going to be a discontinuity where 0 is dividing 0. Okay, so what does this mean? Holes occur when P of X, that's our numerator, and Q of X, our denominator, both equal 0. So Q of X being the denominator of that rational function and P of X being the numerator of that rational function. Right? So when they're both equal to 0, we're going to actually have a teeny tiny hole in our function. Okay. This is not a vertical asymptote. All right, so let's do a couple quick examples of what this looks like or what it could look like, and then we'll take a break, okay? So let's say that I have this example. F of X equals X minus 2 over X plus 1 times X minus 2. Okay, so the example is F of X equals X minus 2 over X plus 1 times X minus 2. Now, I claim that there is a hole and a vertical asymptote in this function. Where, and by where I mean what X value do we think gives us a hole? All right, Dallas, tell us why you say x equals 2 would give us a whole.
I think x equals 2 would give us a whole because if you put in the x value, x2, then the top factor would become, or the top polynomial would become 0, and the same with the bottom, which is equal to that like 0 over 0, leaving just like the 1 over x plus 1.
Nice, nice, nice. So Dallas is correct. There is indeed a whole at x minus 2 equals 0. And in fact, we could even say that that's when x equals 2. That's where the whole is, okay? Now, I think he explained his reasoning fairly well there, but we also kind of can see just by color coding that we have the same factor on the top and on the bottom. If we have the same factor on the top and the bottom, that's going to help us find that discontinuity where we get 0 over 0, okay? What about finding a vertical asymptote? Where, and by where, I mean what x value, do we think that we're going to have a vertical asymptote? Okay. I think those are very valid guesses. We could say that x plus 1 equals 0 or x equals -1 is a vertical asymptote. Then I see your suggestion that perhaps x equals 2 is also a vertical asymptote. And so I purposely asked us to identify the whole first, because as it turns out, we can't have a whole and an asymptote in the same place. So it's either one or the other. And in particular, if we see a factor on the top and bottom, that will always correspond to a whole, whereas the factor that is only on the bottom generates a vertical asymptote. Okay. So I'm going to cross this out real quick, but I'm also going to put up a graph of this so we can see where the vertical asymptote and the whole are coming from, okay? So while I'm switching my screens, if you have Desmos, right, you can go to desmos.com calculator, and you can type in this function, f of x equals x minus 2 over x plus 1 times x minus 2. And I'm going to stop sharing here and then start sharing my other screen. And let's see what we get. All right, so we've got y equals, let's see, x minus 2 divided by x plus 1 times x minus 2. All right, so we should be getting a picture that kind of looks like this, yeah? Now, if we look, we should see a vertical asymptote at x equals -1, right? And I think I can annotate on my own screen here if I can find it. Right, that right there is our vertical asymptote at x equals -1. Right, that blue line that I just dashed in, that's our vertical asymptote. But if we go to x equals 2, that would be like right here. But it looks like it's just a regular function, right? It just looks regular. So how would we know that there's a whole? Well, we can definitely tell there's no vertical asymptote there, right? Because I can't draw a line like this that sort of divides the function into two pieces. Like that's not a thing. But let me clear all the drawings for a moment. So yes, Desmos is a powerful tool, but sometimes we have to make sure we know what we're looking for. Oh, clear all drawings, stop with the annotations. Okay. So I'm going to zoom in, and I suggest that you do the same thing too. You can do that by clicking on the plus button, but I want you to see if you can get as close to 2 as you can, right? So I'm like getting pretty close in there, but it still looks like it's going straight through the line. But one of the features about Desmos, right? So if I sort of zoom back out for a moment, one of the cool features about Desmos is if you click on a point, it tells you what the coordinate of the point is, right? So I have 0, 1 here. This is 1, 1.5 or 1, 0.5. But I want everyone to click on x equals 2 right now, right? So like right around here, if I click 1.98, 2.01, do you see how it just turned it into an open circle right there? 2, undefined, right? So 2, undefined is Desmos's way of saying there is a hole at x equals 2. Now, let's say I wanted to make another hole in the function. What if I did this, x plus 3? How could I make a hole at x equals -3? Right, meaning I want to go here to my function and I want it to say -3, undefined. How could I change the function to make there be a hole at x equals -3?
You
you
can put
put
a
it-
x plus 3 at the denominator.
Yeah.
Perfect, exactly, right? The thing that I colored in the blue earlier, if I have another blue one on the bottom, function still looks the same, but let's zoom in. -3. Oh, there we go. -3 undefined, right? So Desmos is great. Like you can use it to say, oh, I want to graph a function. I want to use a calculator, but you can also use it to help you think about those patterns, right? If I just put x plus 3 in the bottom, so it's not on the top anymore, it's only on the bottom. Guess what I did? I made one vertical asymptote. Vertical asymptote at x equals -1. But as soon as I put the x plus 3 only on the bottom, I made another vertical asymptote. At x equals -3. Right? So use Desmos, play around with it. Like, yes, use it to help you with your homework and your quizzes and stuff, but also to kind of think about it as a studying tool. If you can make a function, you can check your answer right on Desmos as well. And that's pretty cool. Okay. So I want to do one last example before we go on break. So I'm going to stop sharing this screen. I'm going to reshare my, my iPad screen so we can take a look at that. But let me clear this. Let me exit out of the annotation, stop that share. Boop, boop. All right, so let's try one more. Okay, let's try one more. Let's say that we had this. Let's say g of x equals x squared minus 9 over x plus 2 times x minus 3. Okay, so this right here is an example of one way that I could say make the problem a little bit more challenging. Okay, and the reason why it's more challenging is because I did the work in the denominator, right? It's already factored. but we need to factor the numerator so that we can think about where there are holes and where there are vertical asymptotes, okay? And so that's one of the reasons that we've been sort of hitting it heavy with the factoring and completing the square over the last 2 weeks in that 15C class, all right? So x squared minus 9. What does that factor into, my friends?
X minus 3 and then x plus 3.
Beautiful. I hope by the end of the semester, we can all do that confidently and fairly easily, okay? So it's okay if it's not as quick for you right now, but it is something I want us to work for, all right? So we do a little bit of extra work, we factor first, and then we can maybe color code a little bit like we did with our last one. What color should I make the x minus 3? If we're matching it to that f of x1, yeah, we'll make it blue, right? Matching factors on the top and the bottom. That tells us that there's going to be a hole at x minus 3 equals 0, which is just at x equals 3, right? Okay. Where, my friends, are my vertical asymptotes? All right, so in keeping in line with our previous question, maybe we could say that there's a vertical asymptote at x plus 2 equals 0 or x equals negative 2. Right? What about this one? X plus 3. We didn't do anything with that yet. What does that x plus 3 tell us? I would say, okay, yes and no. It tells us nothing about a hole or a vertical asymptote, okay? So in particular, let's kind of zoom in and maybe make a note that this does not tell us about discontinuities. We're just going to abbreviate that. It does not tell us about discontinuities, okay? It does, however, help us figure out end behavior. Okay, so nothing in the sense of nothing that we were just talking about, but it did tell us about something we talked about like 15 minutes ago, which is end behavior. Okay, and so in particular, our g of x is there a horizontal asymptote? And if so, where is it at? All right. We got to compare the degrees, right? We have a second degree up here. This one is a little trickier because we have to think about how we find that degree, but we would take the x and know they make an x squared, which means the degrees are the same, which means that my equation for the horizontal asymptote is going to be a y equals 1 over 1 or just 1. Okay. What's the horizontal asymptote, if there is one, for the f of x that we just looked at?
Do you mean like example 2 on the right?
This one. Does this one have a horizontal asymptote? And if so, where is it at?
It's at 0.
And how
Or
did you,
y equals 0.
yeah, what's the degree on the top, folks? Yep, degree on the top is just 1. Degree on the bottom, 2. Perfect, Ian, right? We've got x and x, which make an x squared. That means that we are looking at the pink case here, where the denominator has a bigger degree than the numerator. And so we end up with a horizontal asymptote of y equals 0. Okay. So lots of different rules, so to speak, but ones that you can definitely use Desmos to kind of play around and see, like, am I remembering the rules correctly or not, right? You can write down a function as a guess and then put it into Desmos to check whether you're right or not, right? So that's pretty cool. You can definitely use the technology for your benefit. All right, so it is 10:41. Let's take a break until 10:56 a.m. All right, so we'll be back here at 10:56. We'll go through some examples here and see how we're feeling about these. But we definitely will be using Desmos. So if you haven't already pulled up Desmos on your computer, if you happen to have one, then I would encourage you to go ahead and do that so that you can use that to help out. Okay, so I'll see you folks back here in about 15 minutes. All right, so in the first part of class, and I'll leave this screen up for a little bit, we talked about end behavior, how we had sort of 4 choices from polynomial end behavior, but for rational functions, when we're looking at the ratio, or when we divide 2 polynomial functions, we actually end up with some other types of end behavior that are possible, okay? Then we talked about things that might happen sort of inside of a function, which is you might have a hole in your function, you might have multiple holes in your function, and we can actually tell where those come from in our equation. And we can also have some other kinds of discontinuities that are more familiar to us, those vertical asymptotes, right? We might have some vertical asymptotes. And again, we can tell from the equation where they come from. And so we're going to use all of this information to figure out a sketch of a graph and figure out how we connect the dots between the first one from the information that we get with some of the other information that we have, okay? And so let's go ahead and get started, all right? All right, so all we have in this entire grid, right? Look at so many blank spots. The only piece of information we have here is a graph or an equation. And so I know I asked you before break to pull up Desmos on your, on your device. But before we do that, all right, because one of the things I noticed is sometimes when I ask people to sketch graphs, it looks very much like you copied it straight from Desmos or a different graphing app. And that's not the purpose of this, right? Like if I'm saying sketch the results and make sure you have important characteristics, those are the ones that we want to make sure we have labeled and all of that. Whereas the other pieces that might be there in a Desmos graph, maybe we don't know those from our function, right? So there's a very fine line between what we know from an equation versus what the graph actually looks like. And it's okay to not have all the pieces, right? Part of this is in sketching something from some information. And so if we take a look at this given f of x right here, all right? We'll notice that that numerator, kind of like that last example we looked at right before break, that's not factored, right? The denominator is already taken care of for us. We've got an x minus 2, we've got an x plus 1, and in fact, we have x plus 1 squared, right? Take a moment, factor that numerator. Let's see what we get. All right, so hopefully we are getting something like what Dallas put in the chat. So an x plus 2 x minus 3. Okay. All right. So let's kind of pause here for a moment. Based on what we have so far, let's start with the discontinuities. All right. What type of discontinuities do you anticipate? Or what type of discontinuities do you expect? Are there going to be holes? Are there going to be vertical asymptotes? How do you know? All right, we have a guess that there's going to be no holes, but yes to vertical asymptotes. And let's see, which color green did we use? Yep. And in fact, we would say maybe that there's 1, 2 vertical asymptotes. All right. We might even want to leave ourselves a note that these two are the same. So same vertical asymptote. Right. All right, well, tell me about end behavior, right? Let's work our way backwards. What do we think, based off of our notes from before, is going to happen at the end? Meaning, are there any horizontal asymptotes or no? And if there are, what might that equation be?
I think it's because the numerator is like the degree is smaller than the denominator, which would make the HA at y equals 0.
Nice. We've got a degree 2 up here. That's, I think, very clear from the way it's written. But the degree down here, this is a degree 3, right? And in particular, it's because we have a squared times a linear. That's going to give us degree 3. Okay. So we've got a degree that on the top that's smaller than the degree on the bottom. And so we're anticipating we might have an end behavior of y equals 0. Okay. So all of that we just learned, right? And so sometimes when we think about all of these boxes on a table, it feels very overwhelming. It's okay to sort of scan down and be like, let me fill in what I know first, right? What do I feel comfortable with? And that's sort of a good test taking strategy to write down something. Writing down something can almost be that way to and through accessing the rest of the question, right? And so we've talked about a lot of these concepts. Let's think about where we want to put them. Degree 2, degree 3, that's going to tell me about end behavior. So let me go down here and answer that question, right? So it says determine whether the rational function has a horizontal asymptote of y equals 0, y equals a number, or a slant asymptote. Then explain your reasoning. And so here's an example of how we might want to write this, okay? We could say, notice that the degree of the numerator is 2, and the degree of the denominator is 3. Then we could say, since the degree of the numerator is less than the degree of the denominator, f of x has a horizontal asymptote at y equals 0. Okay. I know that is a lot of words. And some of you are like, do I really have to write those all out? And I'm going to go with a yes. Yes, you do. Okay. You don't have to use the same words that I use, but I wanted to show you an example, a model of what a strong sentence might be, okay, or sentences. So we're saying, look at the degree of the numerator, it's 2, and the degree of the denominator is 3. And just going back to those rules we talked about earlier, since the degree of the numerator is less than the degree of the denominator, the function has a horizontal asymptote at y equals 0. Okay. So if you're like, I never know how to explain my reasoning, I'm going to try and put some of these examples in here. So hopefully that'll be something to help us think about how to explain things. Okay. All right. Now we had also color coded our function to say that there might be some vertical asymptotes, but that there are no holes. What should I write for discontinuities from a number divided by 0? What do I put there? A number over 0. Let's see, not applicable. Never mind.
From there, you put like the x-intercepts, or not x-intercepts. 1 second. Yeah, or no, the vertical asymptote.
Yeah. So especially as we're doing this for the first few times, I'll go ahead and if I'm learning this for the first time, I'll write number over a 0 equals a vertical asymptote and 0 over 0 gives me a hole. Like for me, that added layer, let me write it one more time, helps me remember it. And it might be something that I even put on that reference sheet. So I don't have to memorize it for the test. It's just already on the reference sheet, right? And so I would agree that we want to put where our vertical asymptotes are. And so if we sort of scroll back up here for a moment, we'll notice that we've got 2 that we colored in this green, x minus 2 and x plus 1. And so I'm going to come down here and say that we have x minus 2 equals 0, and we have x plus 1 equals 0. Which means that there's one vertical asymptote at x equals 2 and another one at x equals -1. Okay, so there are in fact 2 vertical asymptotes. Now, what about the discontinuities from 0 over 0? We didn't have any common factors between the numerator and the denominator. So here we can say no holes since there are no common factors between the numerator and denominator, right? There are no holes, and our reason, so that we don't just kind of guess blindly, like, I'm just going to say there's no holes for no reason. I'm saying there's no holes because there's no common factors between the numerator and the denominator, okay? Now, let's go ahead and actually talk about the domain next, right? I don't know how this group feels yet, but I feel like a lot of times as soon as someone brings up domain, people sort of freeze up and they're like, I don't know. But keep in mind that a domain is just talking about the X values that you can have in your function, okay? So in other words, the domain is asking us what X values, what X values are okay to input into the function. Now, here's the good news. All the discontinuities tell you is the X values that cannot be put into the function. All right, so I wish I had left myself a little bit more space here, but maybe we write it here. Notice that the discontinuities tell us what input values do not work. Right? So we know that we can't put in x equals 2 and we can't put in x equals -1. So here's how we write this, okay? We basically want to say all values except x equals -1 and x equals 2. So we're going to start from -infinity and we're going to go to -1. And we're going to use the parentheses here because we're not including -1. We're going to put a little U symbol. That U means in union with. It's like an and. The piece from -1 to 2. Again, a parentheses because we've got another vertical asymptote. And from 2 to infinity. Okay. This notation says all real numbers except x equals -1 and 2. All right. I want us to understand that, and I want us to know how to write that. Okay.
And you do the same thing if there are holes, right?
Exactly. If there were holes, we would do like another bracket where that hole is and then kind of keep going. Exactly. All right. So I'm going to take the information we have so far, and I'm going to go ahead and start to sketch out some of the things that I consider important characteristics. Okay. So these vertical asymptotes, let's go ahead and draw those in a blue. So we'll say at x equals 2, x equals -1, we're going to draw in our vertical asymptote. So x equals 2, maybe around somewhere here. X equals 1 will be a little, -1 will be a little bit closer there, right? And so we've got our x equals 2, x equals -1. And then we can go ahead and put in our horizontal asymptote, which we said was going to be at y equals 0. All right. I know that doesn't look like much of a graph because we haven't even drawn the function yet. We've literally just drawn a skeleton of what's going to happen here. Okay. The other pieces of information to help us like connect the dots, like literally connect the dots, we're going to go back to the idea of the x-intercept and the y-intercept. Okay. And so I know this was from a few sections ago, but I'm wondering if someone can remind me how we find an x-intercept. I mean, sorry, the y-intercept. Let's start with the y. Good. And so this again is something that like, if I don't know this off the top of my head, I write it down for myself every time so that hopefully it will become sticky in my brain, right? So I'm saying y-intercept means every x is 0. So all I have to do is take my function and plug in 0. That's all I have to do, right? So I'm going to go ahead and plug it into this version up here. Okay, everywhere I see an x, I'm going to plug in a 0, but you could also choose this version as well. Either one would be fine. So I've got a 0 plus 2, 0 minus 3 over 0 minus 2 and 0 plus 1 squared. All right, so I work through this. I'm going to get a -6 on the top, a -2 on the bottom, and so I get a 3 out. But we know we want to write our final answer as a coordinate, so we'll say that our y-intercept is 0, 3. Okay. And as soon as I have that point, I can go ahead and mark it on my graph, 0, 3. Okay. All right. How do we find an x-intercept?
You basically, from my understanding, just don't really pay attention to the denominator and then set the numerator values to like the factors equal to 0.
Okay, maybe before we get there, how do I represent an x-intercept? Yeah, we're gonna have a number, comma 0. And so if you're not sure how to find it, right? Because I think at some point, if anyone tries to approach math as like, let me memorize all the rules, you end up getting to a point where you can't do that anymore because there's just so many rules, right? So part of what I'm trying to infuse in us is like the reasoning part. So we know an x-intercept is a number, comma 0. That means I'm going to take my function and I'm going to set it equal to 0. Like I want a y value of 0. So we can say 0 equals x plus 2 times x minus 3 over x minus 2 times x plus 1 squared. Okay. Now, one really, really, really important thing to note is this. The only way to get a fraction to equal 0 is if the numerator equals 0. Okay, so Let me repeat that one more time. The only way to get a fraction to equal 0 is if the numerator equals 0. And let's convince ourselves with a few numbers here. 0 divided by 1, that's going to give me 0. 0 divided by 2, that give me 0. 0 divided by negative 11, what's that give us? 0, right? And in fact, we can generalize this to say 0 divided by a number is going to equal 0. All right. So what Dallas said earlier is correct. We do want to think about what makes the top part 0. But the reason we're doing that is because the only way to get that fraction equal to 0 is if the top equals 0. And so we'll get x plus 2 equals 0 and x minus 3 equals 0, which gives us negative 2 and a positive 3. And if we write those as coordinates, we'll get negative 2 comma 0 and 3 comma 0. And we can go ahead and plot those here. So we'll get negative 2 somewhere right about here, positive 3 somewhere right about there. I don't actually know anything else about the graph other than this. So if we are like in an exam and I say, I want you to sketch the important characteristics, this is about as far as I expect that you get, right? But do me a favor, go ahead and put this f of x into Desmos now. All right, let's see what Desmos says this looks like, and let's see if it matches the characteristics that we found from our equation. I'm going to stop sharing my screen here, and I'm going to go ahead and share my other screen. So many screens. And when we graph the original function, we get something kind of like this. All right. Now, if I were to go ahead and draw in my vertical asymptote, I would notice that like right around here at x equals 2, there's a vertical asymptote. And there's also one right around here at x equals negative 1. That matches with the blue lines I drew on my graph. And I also said there is a horizontal asymptote at y equals 0. And I can see that the ends of the function kind of flatten out to 0. That's what we mean when we say the end behavior goes to y equals 0. Okay. Now the last, go ahead.
I'm a little confused about the horizontal asymptote because it crosses through like the line on the graph.
Yeah, it does, doesn't it? You mean like, let's see, right here?
Yeah.
Mm-hmm. And it looks like it crosses maybe like right around here too.
Yeah.
Okay. So let me finish finding the intercepts, and then let's talk about the biggest lie that you ever learned about asymptotes. So let me clear. Okay. So where did we find our intercepts? We found an x-intercept at -2, at +3, and we found a y-intercept at 0, 3. So all of those characteristics match up with what we found using the equations, and that's pretty cool. I know that Desmos got to it way faster than we did, but it's really neat to think about why this works and how if we change certain things, it'll change what shows up, okay? So actually, let me clear this for a moment, and let's use Desmos to explore this lie about asymptotes. No more annotation stuff. Okay, so let's clear this out. Let's say y equals x equals y squared. Sideways parabola. Is this a function? Y equals x squared. Is that a function? All right. Why is the green parabola a function, but the blue one is not? Oh, okay. Is this a function? Why? Okay. So how many of you folks have heard of this vertical line test before? Anyone? Anyone? You can give like a quick thumbs up if you have, or all right, so the vertical line test is one way that we can tell whether a function is a function. All right, so all of the pictures that I showed are relations. Okay. However, only 2 of them are functions. All right, so a function is a little bit more strict than a relation. A relation is just like a graph of anything, right? So it's kind of like if you're like hanging out with someone, it's not anything serious, it's a relation. But then like when you put that title on it, like you are my partner, you are my boyfriend, my girlfriend, whatever it might be, my wife, my husband, whatever that title is, that's almost like you're becoming a little bit more serious. That's like a function, like it has another level to it, okay? So this purple one and this green one are both functions. The way we can tell is if we draw a vertical line anywhere. All right, so we draw this vertical line. How many times does that pink line cross the green graph? It crosses 1 time, right? And in particular, it crosses right there. How many times does the pink line cross the purple graph? Once, and in particular, that happens down here. If a function or if a relation, you draw a vertical line and it only crosses it 1 time, then we can call it a function. Right? It's almost like for people who like to be in a relationship with only one other person, right? That exclusive piece, you're saying we're going to be exclusive, so now we're a function. Only crosses 1 time. Okay. However, if I clear this out, okay, clear this out, and I go back to the first one we graphed, right? This is a relation because anything I graph is a relation. However, I don't know that x equals y squared wants to be exclusive, which is fine. Some people don't want to be, and that's something they don't want, right? Whoa, I thought that was going to draw the line for me. It did not. Hold on. Great. Okay, so if we draw a pink line here, we can see that the pink line crosses the relation here and here. Okay, so x equals y squared does not want to be exclusive. We call it a relation. It's still a thing. It's just not a function. Okay. Why am I telling you all about relations and functions? Here's why. Because when we learn about asymptotes, we typically hear an asymptote is a line that a function gets really close to, but never touches or crosses, right? That's usually what we hear when someone says, oh, that's an asymptote. People are not being specific here, okay? When we talk about asymptotes, let me get rid of this picture. Let's go back to y equals x squared minus x minus 6 divided by x minus 2 times x plus 1 squared. Okay, so great question. This, right? If we think about the vertical asymptotes that are happening here, we have one here, and we have another one sort of here, right? And I think we would agree that the function does not cross the vertical. They get really close to the pink vertical asymptotes, but they don't actually cross them. If I had a function, let me turn this off for a moment. If I drew a function that crossed a vertical asymptote, maybe if I crossed the vertical asymptote, that might look something like this, right? You like my, draw like a nursery school child diagram here. So if this were a function, maybe we think, okay, the blue is getting closer and closer to the pink, so the pink line is an asymptote. But is this blue squiggly that I just drew a function or not? It's not a function, right? So when we talk about functions that have vertical asymptotes, we cannot cross a vertical asymptote, then our graph is no longer a function. Okay, we cannot cross the vertical asymptote because then our graph is no longer a function, and we're looking specifically at functions. That's why when people say an asymptote is a line that you get close to but you never really cross, what they really mean is a vertical asymptote is a line that a function gets really close to but never touches or crosses. Okay, so people have been leaving out this word vertical. Here's why this is important. I'm going to pick a different function. Don't worry about the sign. Okay. So we've got this wavy looking thing, right? Hopefully at some point we've seen functions that look kind of wavy like this, but this is actually going to be one that we look at in calculus. All right, and let's sort of zoom out a little bit. What's happening to the waves as we go further and further out? All right, so notice that the waves get smaller and smaller as we go out to the ends of the function. Okay. Now let me zoom back in for a moment. If I were to draw in the horizontal asymptote, that blue line crosses the red curve a lot of times. In fact, it probably crosses more than 10 times in the picture we're looking at, which means that if we zoom out even further, that blue line would continue to cross a bazillion times. But if I were to think about this function, right, and I am crossing the function a bunch of times, a bunch of times, a bunch of times, is this still a function? That is, does it pass the vertical line test? Yes. And so that's sort of the very long answer. You cannot cross a vertical asymptote because then it's not a function anymore, but you can cross a horizontal asymptote. It's more just describing, does it get closer to a specific value or not? That's what we mean when we say y equals 0. Okay, so let's get rid of these extra pictures, right? Let's go back to the picture we were actually looking at. And so I love that observation, the observation that, well, hold on a second. How come it's okay to cross right there? And that is okay because it's still a function. Yes. So Ellie, that's a great summary of this like rant that I've been going on. A function can cross a horizontal asymptote as many times as the function wants to. But we cannot cross a vertical asymptote because then it's not a function anymore. All right, so I'm going to clear this. And if the only thing you take away from what we've just talked about in the last 10, 15 minutes is that you can cross a horizontal asymptote, but not a vertical asymptote, that is absolutely fine, okay? All right, so here's what I'd like to do right now, all right? It is 11:40, and I don't want to take too much time, but I think sometimes it's beneficial to kind of see where you're at in terms of like, what do you know, what do you not know? All right. And so what I'd like us to do is actually go into some breakout rooms for just 10 minutes. Okay. And in those rooms, I want us to look at example 2. Try it together and see what you can answer. Right? In other words, I want you to answer as many things as you can. And it's okay if it's one thing that your group is like, I get this one thing, I don't get anything else. That's okay. It's okay if you're like, oh, I got all of these. That's also okay. But I think the purpose of this is not screens down, microphone down. I don't want to talk with anyone else and I don't want to put myself out there. But it's like, okay, we've talked about a bunch of these things. What do I actually feel confident about? And what just kind of made sense when someone else said it, but I don't think I actually get it. Okay, I think those are two very different levels of learning. So we're going to go into a few breakout rooms right now. Take a look at it for 10 minutes. I'm going to call us back in 10 minutes and let's just see what we know. Okay. And again, it's okay if there's only one thing that you come back as a group and you're like, ooh, I get this, but we don't get anything else. That is totally fine. Okay. So let me pause the recording. All right. Maybe someone from group 1, which was if you were not in this group, in the other group, what are some things, or at least one thing, that you were able to figure out from the picture?
So for the like discontinuity from the pound over 0,
Mhm.
there's a vertical asymptote at 4.
Nice.
So then that means that there is a what is it? X minus 4 on the bottom as well, or on the denominator.
Yes, means x minus 4 is a factor on denominator. Perfect, perfect, perfect. Okay, I love that. We went for some things that maybe were more concrete, right? We can see this vertical asymptote, we can see the whole. Awesome. And actually, from these two, if we put the information that you both shared together, let's take a moment and write out what our domain of this function is. All right, so I'll give you a moment to write out the domain for this function. And then we'll maybe start with the words version first and then move into the symbols version. So all real numbers except what are going to be okay for this function, except 2 and 4. Okay, now I really appreciate that you said 2 and then 4, like in that order. And the reason why I think the order is helpful is because when we write our interval notation, we start at negative infinity and we kind of work our way this way. So if you can arrange these numbers in order from smallest to largest, then you've actually got a good map for what you're going to put in your interval notation. So we'll start at negative infinity and we'll go until 2, which is the first discontinuity. We're going to use the parentheses because we're not including it. And we're going to say in union with, or and, 2 to 4, close it, and 4 to infinity. Okay. All that says is this negative infinity to 2 means this chunk of the graph right here. Okay. The 2 to 4 means this chunk. And then the 4 to infinity, that means this last piece. Okay, so you're just describing the different pieces of the function. That's really excellent work. Are there other, I'll open this up to all groups now. Are there other things that we recognized about this function? It could be yes, it could be no.
I recognize that the horizontal asymptote was shifted down by 4. So that would mean that, like with the denominator rules or the degree rules that we talked about, that the degrees have to be equal and then do some type of ratio.
Okay, good, good. So we're going to go to the horizontal asymptote, which is the end behavior at the very bottom here. And so it says determine whether the rational function has a horizontal asymptote of 0, y equals a number, or a slant asymptote. And we can say this. Since there is a horizontal asymptote at y equals -4, the degree of the numerator must equal the degree of denominator. Okay, so again, we're sort of working backwards here, right? We know that if the degrees are equal, we're going to have a horizontal asymptote of y equals some number. Well, what that means is that if we get a horizontal asymptote at some number, then the degrees must be equal to each other, right? And so the ratio of the leading coefficients should be -4. Okay. I think that is really, really good work. All of this right here, however much of this you felt like you either got in your group or maybe now you're like, oh, that makes so much sense. This is a direct application of what we talked about earlier, but like in a different order, right? But we can use some of this to start to write our function, right? And part of this, again, like this idea, someone says, write a function, and you're like, I don't know, that seems so hard, right? Write down what you have. We know that x minus 2 over x minus 2 is part of it. We know there's an x minus 4 in the denominator. So start there, right? If you don't have anything else, at least you're putting something down that makes sense based off of your findings. So we can say f of x equals, I'm going to put a long fraction line, and I'm going to have my x minus 2 over x minus 2. That gives me the whole that we had here. I'm going to put the x minus 4 in the bottom. So that's where our vertical asymptote is. I wish I knew a little bit more about what was going on up here. I wonder, does the x-intercept or the y-intercept, which one of those do we use the numerator for? Okay, so maybe let's go to the x-intercept one. Let's remind ourselves that an x-intercept is a number, comma, 0, right? All the y values are 0. And so let's see. If I want the y value of this to be 0, and I have an x minus 2 over x minus 2, x minus 4, let's see. What is the x-intercept on this graph? 2, -1. All right, let's see. We zoom in here. Where does the function cross the x-axis, which is right here? And it does look like it's going to be at -1. Okay. So let's take that value. I want to have, when I set just the numerator equal to 0, okay? What would I have to set to equal 0 to get -1 out for my x? Nice. X plus 1. This would give me x equals -1 as an x-intercept. Well, I have x minus 2 on the top, but you know what I don't have? An x plus 1. If I put in x plus 1 in that numerator, that's going to help me make the x-intercept at -1. All right, last piece of this puzzle. What y-intercept do I need to get out? Yeah, I want to get y equals 1 as my y-intercept. How do I find a y-intercept? Everywhere I see x, I'm going to put in 0. So let's see what we have right now. 0 minus 2, 0 plus 1, 0 minus 2, 0 minus 4. What does that give me if I just plug in 0 right now? All right, we get -2/8. What can we reduce that to? -1/4. Okay, so the way it stands right now, if I plug in 0, I get -1/4. But what I want to get out is 1. What can I do to -1/4 to make it into a +1? Yeah, if I multiply it by -4, I'm going to get -1. So the last step, which I think is really tricky, right? We want to make sure it satisfies all of these things, is if we write it this way, we're going to get most of the things, but we're going to get the wrong y-intercept. The only thing we need to do is multiply it by a -4. This part gets the correct y-intercept. Okay, this -4 makes it so that we get the correct y-intercept. But you know what it also does? Whoops. Let's check out our coefficients now. The coefficient on the top is -4. The leading coefficient on the bottom is 1. -1 divided by -4 gives me the horizontal asymptote that we were looking for. All right, so it's like the final piece of the puzzle that makes everything about this picture true. All right. Now, before we start to panic a little bit, like maybe you felt like the first part of the lesson today went well, and the second part you were like, oh, I don't know. I think the most important things I want us to walk away with are how do we, from the graph, figure out the discontinuities and the end behavior. Okay, so if those are things that you felt confident about, whether it was in the small group rooms or when we came back together as a whole group, discontinuities, horizontal asymptotes, that is someplace we all definitely want to feel comfortable with. Okay, I think that this part right here is more of like an extension challenge kind of situation where I think being able to reason through it is really valuable, but more like icing on the cake, so to speak. Okay. I think I do ask you to do one question similar to this on the quiz. I would encourage you to work on those questions together because I think sometimes talking it out with other people is way more helpful than just trying to do it on your own. Okay. And there's also tutoring or office hour sessions if you want a little bit of help walking through that. Okay. All right. Now, maybe just to end on a more positive note, I want to take a very brief look at example number 3. Okay, so we're not going to go through all of it, but again, I sort of want to highlight the parts that I think are most important to walk away from today's lesson with. All right, so in example 3, we've got some information, we've got some x-intercepts, a y-intercept, discontinuities, and that's it, right? But we don't have a graph, we don't have a function, we don't have a domain, we don't have the end behavior. So I want you to take a look at this right now, and I want you to think about what is one thing that you think you could answer, one box that you could fill in here. And take a moment and do that, right? And maybe in about 1 or 2 minutes, let's come back together and see what felt most accessible to us, right? So look at this, see what feels like, oh, I could make this connection. No matter how small I think it is, it's a connection that I feel comfortable making from what we've covered today. All right. Anybody feel like there's something they're like, yes, I was able to apply this from what we learned today?
One of them that I did first, I guess, was just graph like the x-intercepts, the vertical isotopes.
Okay, great. So like all these pieces of information here, just kind of put them on the graph.
Yeah.
Okay, love that, love that. Ellie, it looks like you said there were no common factors. Tell us how you knew that.
Because it says discontinuities from 0 over 0 is none, and that means there are no holes So we don't put any common factors when we write the function.
No common factors between the numerator and denominator. Love it. Love those connections. All right, so we could graph some of these points. Negative 3, 0, positive 3, 0, negative 18/4, and maybe a vertical asymptote here and here. Okay. All right. Was anyone able to write the domain for this? Do we think we have enough information to do that?
Yes. I think it's negative infinity to -2, and then 2 to, was that 3? No, yeah, 2 to -3, and then -3 to +2. Or wait, 1 second.
Okay, no worries.
Okay, yeah, I got negative infinity to -2, union -2 to 2, and then union 2 to positive infinity.
Yeah, looks great. And maybe just to clear up where those came from, right? The -2 is one of the vertical asymptotes that we have. And this +2 is from a different vertical asymptote, right? So since those are vertical asymptotes, they cannot be included in our domain, right? So these are all the values that work, which means we can just take all the values that don't work and sort of cut them out of our domain. Okay. All right. One last question for you today. What do we think about the end behavior? What is the end behavior? Or do you think we don't have enough information to figure it out?
Wouldn't we need to like write the function to see or like determine what factors from the x-intercept and y-intercept we can get?
Yeah, I would agree. I think that at this point, not enough information, right? Which means that if you wanted to make a function that had a horizontal asymptote of y equals 0, what would you make true about the degrees of your numerator and denominator?
That the numerator is larger than the denominator.
Close. Degree of the numerator is going to be less than the degree of the denominator. Right. So if we want a horizontal asymptote of y equals 0, we want the bottom to overpower the top, meaning there's a higher degree in the bottom. But when we get a horizontal asymptote of y equals a number, we want the degrees of numerator and denominator to be equal. Okay. And then That last case is when the top overpowers the bottom, or the numerator degree is higher than that denominator degree. Okay. Now this idea right here of end behavior and this idea of discontinuities, we're actually going to come back to again in calculus, right? So if anyone in here has ever taken calculus, we'll be looking at end behavior and discontinuities through the lens of something we call limits, okay? So if you've ever taken calculus or you've heard limits before, we're going to come back to this in about 6 months, and we're going to look at this through a different lens. But I promise you that if these are things that you remember from 116, it's going to make your life easier in Math 150. Okay. So if you want to, feel free to try and write a function here that matches the rest of this. Okay, I think it takes a little bit of playing around with things to make sure the numbers work out. But the most important takeaways, I think, are right here, which is put down what you know, make the connections between things, and don't always ask yourself the same question in the same order. Maybe switch up the way you ask your questions so that you can think about, okay, this is how I understand the concept and I can get to that answer in more than one way. All right. So folks, that is the end of 3.7. So I'm going to go ahead and stop our recording here.